Hello again, ladies and gentlemen. So I have here what's called a spring scale. All right, and the spring scale obviously measures, in this case, it's the weight, right? Okay, of this 100-gram mass, and we can see that on the left side we have the force in newtons, and this 100-gram mass multiplied by the acceleration due to gravity should be about 0.98 newtons, and that's just what we see. But we'll see that the spring scale reads something a little bit differently when the object is accelerating upwards. I don't know if you can see that on the video, but if the object accelerates upwards, something changes. And if the object accelerates downwards, it changes also in a different way. Okay? So, go back to our scale here, and what does the scale measure? Well, the scale measures a normal force, right? It doesn't measure a weight. Well, what we can see too is that if I'm in free fall, okay, and this is in free fall, and I somehow can manage to get it under my feet, what is the normal force going to be on it if we are both in free fall? Well, zero. It's going to be nothing. There's going to be no normal force, right? Because it's not going to be pushing back against me if we're both falling at the same rate. Now, if I'm standing on the scale in an elevator and the elevator starts to accelerate upwards, okay? Now, you've all felt this on the elevator. When the elevator accelerates upwards, you feel almost kind of pulled down, almost like your weight has increased. This is something we call apparent weight. Man, I hope I spelled weight correctly. I before E, E before I, it's a hard one there, okay? Now, the apparent weight is the weight that you appear to have. Now, remember that weight itself is always defined, right? That is the force exerted on an object due to gravity, okay? And that doesn't change because the acceleration due to gravity doesn't change. But the weight that you appear to have, we've seen, can change. All right, you can either appear heavier or you can appear lighter than you are. It depends on whether you are accelerating against the force of gravity or if you're accelerating with the force of gravity. Note with the spring scale that starting here with the weight, we've got it like so, but if it accelerates upwards, we'll see that the inertia of this kind of takes a second, and right, it has to pull upwards, and the thing that's measured, the pull upwards, is the apparent weight in this case. All right, if it accelerates downwards, then the object is not accelerating as quickly due to the acceleration of gravity. Then we can see that it should be a little bit less than what it is. Now, we normally experience this with the scale that you would stand on. So it's much easier to think of this, that essentially the weight, the apparent weight of a person or object is equal to the normal force in magnitude. All right, so we'll call it WAP is equal to the normal force in magnitude. Again, they're not the same thing quite, but that's what they are. Okay. So we can see this through an example. We've got our example here. We're skipping to this one where it says, what is the apparent weight of a 20 kilogram object in an elevator with an acceleration of 4 meters per second squared downward, 4 meters per second squared upward, 9.80 meters per second squared downward, and g upwards again. So let's take a look at this. Again, we'll start with a free body diagram. So here's the person. Don't forget, the person's weight is here. It's equal to their mass times the acceleration due to gravity. And this is constant where we are at Earth's surface. Okay. Now, what we've got in our first case is we've got an acceleration downward. So the force exerted on the person upward, the normal force, which, if the person is standing on a scale, right, is the weight of the person or the apparent weight of the person, it's less than that due to gravity. It has to be if it's accelerating at 4 meters per second squared downward. Okay? Now, again, it's the same way to solve this as it is anything. First, we'll add up the forces on the object. We've got the normal force in the upward direction and the weight of the object in the downward direction. Once we've got those, we see that the object is accelerating in this case, and the object has an acceleration in the downward direction. And that acceleration is, well, in this case, we'll take down as the negative direction, and we'll say it is negative 4 meters per second squared. So we'll use that when we're solving here. So next, Newton's law tells me that I can find the summation of the forces with mass times the acceleration of the object. And we'll see that the normal force is equal to the weight plus the mass times the acceleration. Now, is this greater than or less than the actual weight of the object? We saw with our spring scale that if the object is accelerating downwards, we'll see the spring scale tend to go smaller than the weight. Okay. Now, is this one less than the weight? Well, yes. When we put negative 4 meters per second squared in for the acceleration, we will see, yes, this is definitely less than the actual weight of the object. So the normal force that would be pushing upwards, the apparent weight, is going to be less than the weight of the object in this case. We can put some numbers in here. Let's even go a little step further and say that the weight is equal to m times g. And notice that one thing we can do is factor out that m from that equation. Even more so now, we can see that this is going to be 9.8 minus 4 meters per second squared. What number do we get for that? I don't know. All right. Now, we'll see that we have the same situation when the object is accelerating upwards. Mathematically, it looks just the same as it did before, right? The big difference, though, is the acceleration. We'll see that one thing, the normal force is no longer less than the weight. If it is accelerating upwards, then the normal force has to be greater than the weight. Yeah, greater than the weight. Okay. The acceleration now is in the upward direction. And it is positive 4 meters per second squared. Well, notice the derivation is all the same, right? The normal force is in the upward direction, weight is in the downward direction. Okay, we get here. And we get here, and now we're putting a positive value in for this acceleration, which means that the normal force experienced, what the scale reads, right, the apparent weight, is going to be greater than the actual weight, because what we have here is greater than g. Okay, so we've got that. Now let's put in a couple different scenarios here. Okay. One of which is part C, where the acceleration is 9.80 meters per second squared downward. Okay, well, the object is in free fall at this point. Okay, so we still are going to end up using this analysis in the end, but we want to see, okay, what happens when we put in an acceleration downwards of 9.80 meters per second. So, all right, now I'm putting negative g. Remember that generally when we're calculating the weight, g is always positive, okay? Positive 9.80 meters per second squared. In this case, it's an acceleration downwards, so I'm using the opposite of the magnitude of the acceleration due to gravity. Well, if I insert that into the equation here, and I should have used brackets. Well, what happens to this right here? We've got, well, it's 0. The normal force from the elevator, which is in free fall, which is a very dangerous situation, makes it so that the apparent weight of the person is 0. They appear weightless. They are in free fall, right? Which is just what we would have expected, all right? Now, the other option that we looked at was when the acceleration is in the upward direction at 9.80 meters per second squared. Let's see, we'll have in this case, A is equal to a positive value of g. In this case, we'll replace that there. So Fn is equal to mg plus our positive value of g. And when we solve this, we'll see that the normal force is equal to m times 2g. And we'll see, let's factor that 2 out. So the normal force, or the apparent weight, is 2 mg. But remember that mg, the mass times the acceleration due to gravity, is just the weight of the object. So if the object is accelerating upwards at a factor of g, that means the apparent weight of this object is 2 times the actual weight of the object.